Welcome to GKE Network Engineering. Welcome everyone. Today we're diving deep into Google Kubernetes Engine from a network engineer's perspective. This is absolutely crucial for anyone preparing for the GCP Professional Cloud Network Engineer certification. We'll start by understanding why IP addressing is the foundation of everything in GKE, unlike traditional virtualization where you might have simple virtual machine to virtual machine communication. Kubernetes introduces multiple layers, nodes, pods, and services, each requiring their own IP addressing scheme. The key insight here is that GKE uses VPC native networking, which means all these different IP addresses come from your VPC's IP ranges. This gives you incredible flexibility but requires careful planning to avoid the nightmare of IP conflicts. Think about this. In a large enterprise, you might have multiple GKE clusters across different regions, plus traditional virtual machines, plus on-premises networks connected via VPN or interconnect. One wrong IP allocation and you could break connectivity across your entire infrastructure. Three critical IP ranges. Let me walk you through the three distinct IP ranges that every GKE cluster requires. This is where most people get confused, so let's be very clear about what each one does. First, your nodes are just regular compute engine virtual machines. They get IP addresses from the primary subnet range. This is straightforward and works exactly like any other virtual machine in your VPC. But here's where it gets interesting. Pods and services need their own IP addresses, and these come from secondary IP ranges on the same subnet. This is what we call VPC native networking or IP aliasing. The pod's range needs to be huge because each node pre-allocates a /24 block for its pods. If you have 100 nodes, that's 100 /24 blocks you need from your pod's range. The services range is smaller because services are just virtual IPs for load balancing. You don't create services as frequently as pods. The critical rule: these three ranges cannot overlap with each other or with any other network you might connect to. VPC native architecture deep dive. Now let's understand what makes VPC native networking so powerful. In the old days, we had something called routes-based networking where pod IPs were hidden behind NAT. That created all sorts of problems. With VPC native, every pod gets a real IP address from your VPC. This means a pod running in your GKE cluster can directly communicate with a virtual machine in the same VPC, or even with your on-premises server via VPN, using its real IP address. The magic happens through something called alias IP ranges. When you create secondary ranges on your subnet, those IP addresses become alias addresses that can be assigned to resources other than the primary virtual machine. This also means your VPC firewall rules work directly with pod IP addresses. Your VPC flow logs can track pod-level traffic. It's like pods are first-class citizens in your VPC network. From a network engineering perspective, this eliminates the black box problem. You can see and control exactly how traffic flows through your cluster. Creating the foundation. VPC and subnet. Let's start building our GKE-ready network infrastructure. I always recommend starting with a custom mode VPC because it gives you complete control over your subnets and IP ranges. The first command creates our VPC in custom mode. Auto mode would automatically create subnets in every region with predefined ranges, but that's not what we want for production. Then we create our subnet with both primary and secondary ranges. Notice how we're defining three different IP ranges right from the start. This is critical planning. The primary range 10.10.0.0/24 gives us 254 usable IP addresses for nodes. The pod's secondary range 10.10.2.0/14 gives us over IP addresses for pods. The services range 10.10.1.0/20 gives us over 4,000 IP addresses for services. See how we're using different octets. The nodes use 10.10.0.x, services use 10.10.1.x, and pods use 10.10.2.x through 10.10.5.x. This makes troubleshooting much easier when you can immediately identify what type of resource an IP belongs to. Cluster creation with explicit IP control. Now we are creating the actual GKE cluster, and notice how we explicitly reference the secondary ranges we created. This is where the magic happens. The cluster IPv4CIDR parameter activates the pod's secondary range. We specify /14 to match what we defined in our subnet. The service's IPv4CIDR activates the service's secondary range with /20. Here is something important. We are not creating a GKE subnet versus a regular subnet. It is the same subnet, but GKE is using the secondary ranges for pods and services while regular virtual machines would use the primary range. The enable IP alias flag is what enables VPC native networking. Without this, you would get the old routes-based model where pod IPs are hidden. Notice we specify both network and subnetwork. The network is the VPC, and the subnetwork is the specific subnet within that VPC where our nodes will live. This gives us complete visibility and control over our IP addressing from day one. Public versus private. A critical decision. This is one of the most important architectural decisions you'll make for your GKE cluster. Let me explain why the choice between public and private clusters is so critical from a security and network perspective. Public clusters are the default, and they're fine for development, but think about what public means. Your nodes get external IP addresses, which means they're directly reachable from the internet. Your control plane has a public endpoint. From a network security perspective, this is a significant attack surface. Even if you have firewalls, you're still exposing infrastructure to the internet that doesn't need to be there. Private clusters flip this around completely. Nodes get only internal IP addresses. The control plane uses a private endpoint accessible only from your VPC. But here's the trade-off: private clusters require more networking setup. You need Cloud NAT for internet access, private Google access for reaching Google API, and you need to think about how administrators will access the cluster. For production workloads, especially in regulated industries, private clusters are almost always the right choice despite the additional complexity. Public cluster traffic flow. Let's trace through exactly how traffic flows in a public cluster. Understanding this traffic flow is crucial for troubleshooting and security planning. Your admin laptop connects directly over the internet to the public control plane endpoint. The control plane authenticates your kubectl commands and sends instructions to the nodes. Nodes communicate back to the control plane over the internet using their external IP addresses. Pod-to-pod traffic within the cluster uses the internal VPC network. When pods need to reach the internet, for example to pull a container image or call an external API, they can go directly through the node's external IP address. For reaching Google APIs like cloud storage, pods can either go over the internet or use private Google access if you've enabled it on the subnet. The key security concern here is that every node is internet reachable. Even with firewall rules, you're depending on those rules being configured correctly and never having misconfigurations. Load balancers can expose services directly to the internet, which might be what you want for web applications. Private cluster architecture. Private clusters completely change the network architecture, and understanding this is essential for the network professional exam. The key insight is that nodes have only internal IP addresses. This immediately eliminates the biggest attack vector: direct internet access to your worker nodes. The control plane uses a private endpoint, which is implemented through VPC peering. Google creates a separate VPC for your control plane and peers it with your project's VPC. But this creates new challenges. How do nodes reach the internet for pulling images? That's where Cloud NAT comes in. It provides source NAT for outbound connections. How do nodes reach Google APIs? Private Google access routes traffic to Google services through special internal IP ranges like 199.36.153.8/. How do you manage the cluster? You need either a bastion host in the VPC, or connectivity from on-premises via VPN or interconnect. The result is a much more secure architecture, but one that requires careful network planning, creating a production-ready private cluster. Let me walk through this private cluster creation command because every parameter here is critical for production deployments. The Enable Private Nodes flag ensures nodes get only internal IPs addresses. This is the foundation of private cluster security. Enable Private Endpoint makes the control plane accessible only from your VPC. No public IP for the master. The master IPv4 CIDR is crucial. This is a /28 range that Google uses for the control plane in their peered VPC. It cannot overlap with anything in your VPC. Enable Master Authorized Networks lets you restrict access to the private endpoint to specific IP ranges within your VPC. Even though it's private, you might want to limit access to just your bastion subnets. Notice we're still specifying the same secondary ranges for pods and services. The private/public choice affects how nodes connect to the internet and control plane, but the pod and service IP addressing works exactly the same way. This creates a cluster that's completely isolated from the internet but still fully functional through careful use of Cloud NAT and private Google access. Node pools and advanced IP management. Now let's talk about node pools and how they affect your IP addressing strategy. This is where things get really interesting from a network design perspective. You can have multiple node pools in the same cluster, and each node pool can even be in a different subnet. This gives you incredible flexibility for workload isolation. Maybe you want your web tier in one subnet with different firewall rules, and your database tier in another subnet with more restrictive access. Different node pools make this possible. But here's the key point. Even though nodes can be in different subnets, the pod and service IP ranges are cluster-wide by default. All pods across all node pools share the same secondary IP range. There's an advanced feature called multi-pod CIDR that lets you assign additional pod IP ranges to specific node pools, but that's usually only needed for very large clusters or special isolation requirements. The network engineering principle here is that you have fine-grained control over where nodes live, but pods form a flat network across the entire cluster unless you implement network policies for segmentation. Control plane endpoints overview. Now we're moving into one of the most critical architectural decisions for GKE clusters: how you expose the control plane endpoint. This decision fundamentally affects how administrators access your cluster and how secure your infrastructure is. The control plane is where the Kubernetes API server lives. Every kubectl command you run goes to this endpoint. Every node in your cluster communicates with this endpoint. So the question is, should this endpoint be accessible from the internet, or should it be private? This isn't just about convenience versus security. It's about understanding the complete network architecture implications. A public endpoint means anyone with the right credentials can manage your cluster from anywhere on the internet. A private endpoint means you need to design your network to provide access paths. From a network professional exam perspective, you need to understand not just how to configure these options, but when to choose each one and what additional infrastructure you need to support your choice. Let's dive into the details of each approach and see how they affect your overall network design. Public control plane deep dive. Let's start with public control plane endpoints because they are the default, but that does not mean they are simple from a security perspective. When I say public, I mean the control plane gets a public IP address that is reachable from the internet. But Google does not just expose this to the entire world. There are important security controls you need to understand. First, there is always authentication and authorization. Even with a public endpoint, you still need valid credentials and appropriate RBAC permissions. But that is application layer security. At the network layer, you have authorized networks. This is crucial. It is a list of CIDR blocks that are permitted to reach the control plane. Traffic from any other IP range gets blocked at Google's network edge before it even reaches your cluster. The key insight here is that public does not mean unprotected, but it does mean you are depending on these controls being configured correctly. One misconfiguration in your authorized networks and you could accidentally expose your control plane to the entire internet. From an operational perspective, public endpoints are much easier for distributed teams, but they require very careful management of those authorized networks. Public endpoint network flow analysis. Let's trace through exactly how network traffic flows when you're using a public control plane endpoint. Understanding this flow is critical for troubleshooting and security planning. Your admin workstation, whether it's your laptop, a CI/CD system, or a jump box, connects directly over the internet to the public control plane endpoint. The traffic is HTTPS, so it's encrypted, but the path is through the public internet. Google's Edge network checks the source IP against your authorized networks list. If the source IP isn't in an authorized range, the connection is dropped immediately. You won't even see it in your cluster logs. If the IP is authorized, the traffic reaches the control plane, which then performs Kubernetes authentication and authorization. This is where your Google Cloud credentials and RBAC policies come into play. Meanwhile, your cluster nodes also communicate with this same public endpoint. They use their external IP addresses to reach the control plane over the internet. This node-to-master communication is how the nodes receive pod scheduling decisions and report their status back. The security consideration here is that both your admin traffic and your node traffic are flowing over the public internet, even though they're encrypted. Private control plane architecture. Private control plane endpoints completely change the network architecture, and this is where it gets really interesting from a network engineering perspective. Instead of a public IP, the control plane gets a private IP address in a special Google-managed VPC. But here's the clever part. Google creates a VPC peering connection between this Google-managed VPC and your project's VPC. This means the control plane appears to be inside your VPC network, even though it's actually running in Google's infrastructure. You can reach it using private IP routing, just like any other resource in your VPC. The master IPv4 CIDR parameter defines the IP range that Google uses for your control plane within this peered VPC. It's a /28 range, so just 16 IP addresses, but it cannot overlap with anything in your VPC. This architecture means that access to the control plane is limited to traffic that can reach your VPC through private networking, either from within the VPC itself, or from connected networks via VPN or interconnect. It's a much more secure model, but it requires you to design access paths for administrators and any automation systems that need to manage the cluster. Private endpoint access patterns. Let me walk through the different ways you can access a private control plane endpoint, because this is where network design becomes critical. The most common pattern is a bastion host, which is a virtual machine within your VPC that serves as a jump server. Administrators SSH to the bastion, and then run kubectl commands from there. The bastion can reach the private control plane because they are in the same VPC. For automated systems, Google Cloud Build and Cloud Shell automatically have access to private endpoints because they run within Google's network infrastructure, which can reach your VPC. If you have on-premises administrators, you can extend access via Cloud VPN or Cloud Interconnect. Your on-premises network connects to your VPC, and routing allows your on-prem users to reach the private control plane endpoint. You can also enable both private and public endpoints simultaneously. This gives you the security benefits of private networking for internal access, while still allowing controlled public access for specific use cases. The key is designing your access patterns before you create the cluster, because changing from public to private endpoint later requires recreating the cluster. Implementing private control plane. Now let's look at the specific commands for creating a private control plane endpoint, as every parameter here has important implications. The Enable Private Endpoint flag is what creates the private endpoint. Without this, even if you have private nodes, your control plane will still be public. The master IPv4 CIDR is crucial. This defines the IP range that Google uses for your control plane. Remember, this is in Google's VPCE that pairs with yours, so it's not taking up space in your VPCE, but it cannot conflict with your VPC's ranges. I recommend using something from the RFC 1918 range for this, as most organizations use RFC 1918 for their main VPC's ranges. A /28 gives Google 16 IP addresses, which is plenty for the control plane. The Enable Master Authorized Networks flag might seem redundant with a private endpoint, but it's still useful. Even though the endpoint is private, you might want to restrict access to only certain subnets within your VPCE. Maybe just your Bastion subnet or your DevOps subnet. Don't forget that private control planes require additional setup. You need private Google access enabled on your subnet so nodes can reach Google APIs, and you might need Cloud NAT for internet access. GKE Autopilot versus Standard Overview. Now let us shift gears and talk about one of the biggest decisions you will make when creating a GKE cluster: Autopilot versus Standard mode. This choice fundamentally affects how much control you have over the underlying infrastructure. From a network engineer's perspective, this is not just about operational differences, it is about what level of networking control and customization you can achieve. Standard mode gives you complete control over the nodes. You manage the node pools, choose machine types, configure networking settings, and can even SSH to the nodes if needed. You are responsible for the entire infrastructure stack. Autopilot mode abstracts away the node layer entirely. Google manages the nodes for you. You just deploy pods and Google provisions whatever infrastructure is needed to run them. You pay for the resources your pods consume, not for the underlying virtual machines. The networking implications are significant. In standard mode, you can use host network pods, customize node networking, and have full control over how traffic flows. In Autopilot, you are limited to pod-level networking, with VPC native being mandatory. Let me show you exactly what this means in practice. Standard mode networking control. In standard mode, you have complete control over the networking stack, and this gives you both power and responsibility. You can choose whether to use VPC native networking or the older route-based model. You can configure custom node networking settings, use host network pods that share the node's IP address, and install custom CNI plugins. For security, you can implement node-level controls, custom firewall rules, and even modify the node operating system. You can use daemon sets to deploy networking agents on every node. From an IP management perspective, you control exactly how many nodes you have and what machine types they use. This affects your IP consumption patterns. Larger nodes can run more pods, which affects how quickly you consume your pod IP range. You also get to choose your upgrade strategy, maintenance windows, and can even run different node pools with different networking configurations within the same cluster. But with great power comes great responsibility. You're responsible for security hardening, OS patching, node scaling, and ensuring your networking configuration doesn't break anything. This is the right choice when you need maximum flexibility and control, especially for complex networking scenarios or when you need to integrate with existing network security tools. Autopilot networking constraints and benefits. Autopilot takes a completely different approach. It removes node-level control in exchange for operational simplicity and built-in security hardening. VPC native networking is mandatory in Autopilot. You cannot use routes-based networking, and you cannot use host network pods. All networking happens at the pod level using the secondary IP ranges we discussed earlier. Network policies are enabled by default and cannot be disabled. This means you get micro-segmentation capabilities out of the box, but you cannot choose a different network policy implementation. You cannot SSH to nodes because you do not manage them. You cannot run privileged pods or daemon sets that modify node networking. Google handles all the underlying networking configuration. But here's the benefit. Google implements security best practices by default. Shielded GKE is enabled. Workload identity is configured, and the nodes are hardened according to Google's security standards. From a network perspective, autopilot clusters are more predictable. The networking configuration is standardized, which makes troubleshooting easier and reduces the chance of misconfigurations. The trade-off is flexibility versus operational simplicity. If your workloads can run within autopilot's constraints, you get a much simpler operational model. Making the standard versus autopilot decision. How do you choose between standard and autopilot? From a network engineering perspective, it comes down to your specific requirements and how much control you need. Choose standard when you need custom networking configurations, when you're integrating with existing network security tools, or when you have workloads that require host network access or privileged containers. Standard is also the right choice when you need to run daemon sets for networking agents, when you need specific machine types or GPU configurations, or when you need to comply with regulations that require specific security controls at the node level. Choose autopilot for stateless web applications, microservices, and batch jobs where you don't need node-level control. It's particularly good for development teams who want to focus on their applications rather than infrastructure management. Autopilot is also excellent when you want Google's security best practices implemented by default, when you want predictable networking behavior, or when you want to pay only for the resources your pods actually consume. From a network exam perspective, remember that both modes use the same VPC native networking fundamentals we discussed earlier. The difference is in the level of control and customization you have over the infrastructure layer. The key is matching your choice to your requirements rather than just picking the easier option. Advanced IP addressing strategy. Now we're moving into advanced IP addressing strategies that can make or break your enterprise GKE deployments. This is where network engineering really separates the experts from the beginners. The fundamental challenge is this: as your organization grows, you'll have multiple VPCs, multiple GKE clusters, on-premises networks, partner networks, and maybe even acquired company networks that all need to communicate. One IP conflict can break everything. We've already covered the basics of node, pod, and service IP ranges. But now we need to think strategically about how to allocate these ranges across your entire organization to prevent conflicts and enable seamless connectivity. This isn't just about avoiding overlaps. It's about creating an IP addressing scheme that scales, supports growth, and makes troubleshooting easier. When you see an IP address, you should immediately know whether it's a node, pod, service, and which cluster it belongs to. We'll look at enterprise-scale allocation strategies, examine real-world conflict scenarios, and learn how to design IP schemes that work for organizations with hundreds of clusters and complex hybrid connectivity requirements. RFC 1918 Standard Approach. Let's start with the standard RFC 1918 approach because this is what most organizations begin with, and understanding its limitations is crucial for making informed decisions. RFC 1918 defines three private IP ranges. RFC 1918. These are guaranteed not to conflict with any public internet addresses, which makes them safe for private networks. The RFC 1918 range is particularly attractive because it's huge, over 16 million IP addresses. You can easily carve this up into regional blocks, cluster blocks, and different IP types while still having room for massive growth. I typically recommend using different major octets for different purposes. For example, 10.0.x.x for production US clusters, 10.1.x.x for production EU clusters, 10.100.x.x for development environments, 10.200.x.x for on-premises networks. Within each cluster, you can use the same pattern. .0 subnet for nodes, .1 subnet for services, .2 to 5 subnets for pods. This creates a predictable, scalable addressing scheme. But here's the problem. Everyone uses RFC 1918, especially the RFC 1918 range. When you try to connect to a partner's network, or when you acquire another company, there's a very high chance of IP conflicts. The IP conflict problem. Let me show you a real-world scenario that happens all the time in enterprise environments. This is exactly the kind of problem that network engineers need to anticipate and solve. Your company has been happily using RFC 1918 for your GKE clusters. Everything works great internally. Then your company acquires another company, and you need to establish connectivity between your networks via VPN or interconnect. Surprise! The acquired company is also using RFC 1918, and their IP allocations overlap with yours. Maybe they're using 10.1.0.0/16 for their production environment, and you're using the same range for your European clusters. Now you have a serious problem. You can't route between the networks because the IP ranges are ambiguous. Is 10.1.1.5 a server in your EU cluster or a server in their data center? The routers don't know. Your options are all bad. Complex NAT configurations that break end-to-end connectivity, renumbering one of the networks which is extremely disruptive, or maintaining separate network islands which defeats the purpose of the acquisition. This is where understanding alternative addressing strategies like PUPI becomes critical. But it also shows why IP planning needs to happen at the organizational level, not just the individual cluster level. PUPI. Using public IPs privately. PUPI. Privately used public IPs. Is Google Cloud's elegant solution to the IP conflict problem. The concept is brilliant. Instead of using RFC 1918 ranges that everyone else uses, you use public IP ranges that you'll never need to communicate with. The key insight is that you don't own these public IP ranges, but you're using them internally in your private network. This dramatically reduces the chance of conflicts with other organizations. For example, instead of using 10.1.0.0/16 for your GKE cluster, you might use 75.75.75.0/24. This is a real public IP range owned by Comcast, but you're using it privately within your VPC. The trade-off is critical to understand. By using 75.75.75.0/24 privately, your virtual machines and pods cannot communicate with the real 75.75.75.0/24 on the public internet. Google Cloud blocks this traffic to prevent routing confusion. So, you need to carefully choose PUPI ranges that your organization will never need to reach. Don't pick ranges owned by major cloud providers, CDNs, or services you might need to access. When done right, PUPI eliminates IP conflicts while maintaining all the benefits of direct IP connectivity. It's particularly valuable for organizations with complex hybrid networking requirements. PUPI implementation strategy. Let me walk through a practical PUPI implementation, because the details matter enormously for success. First, you need to select appropriate public IP ranges. I recommend using ranges from geographic regions or ISPs that your organization has no business relationship with. For example, if you are a US company, consider using IP ranges from specific international ISPs. The subnet creation process is identical to RFC 1918. You just specify the PUPI range instead. But here is the critical step. You must enable private Google access on any subnet using PUPI ranges. Why? Because your virtual machines have PUPI addresses, they cannot directly reach Google APIs over the internet. Private Google access provides an internal path to Google services using special IP ranges like 199.36.153.8. This is actually a security benefit. Your PUPI-addressed virtual machines cannot accidentally reach unauthorized internet destinations, but they can still access Google Cloud services they need. The routing implications are important too. Your VPC routes will now contain PUPI ranges, and these need to be carefully managed when advertising routes to on-premises via cloud router. Documentation becomes critical with PUPI. You need to maintain clear records of which PUPI ranges you are using and why, so future network engineers understand the design decisions. Subnet planning at enterprise scale. Now let's talk about subnet planning strategies that work at enterprise scale. This is where you need to think like a network architect, not just a cluster administrator. The key principle is hierarchical allocation. Start with large blocks and subdivide them systematically. For example, allocate a /12 for each major business unit, then /16 blocks for each region within that business unit, then /20 blocks for each environment, and finally /24 blocks for specific purposes. I recommend creating a subnet naming convention that reflects this hierarchy. Something like BU Region ENV Purpose. For example, FinTech US Central 1 Prod GKE nodes. For GKE specifically, plan for significant growth in your pod IP ranges. Pods are ephemeral and numerous. A single node might run 50 plus pods, and you might scale to hundreds of nodes. Always allocate much larger pod ranges than you think you need. Consider using alias IP ranges strategically. You can create multiple secondary ranges on the same subnet for different purposes. Maybe one for GKE pods, another for serverless connector, another for future services. Document everything in a central IP address management (IPAM) system. This isn't optional at enterprise scale. You need to track every allocation, prevent conflicts, and enable other teams to request IP ranges without causing problems. IPv6 in Google Cloud Overview. Now, let's move into IPv6, which is becoming increasingly important as organizations run out of IPv4 addresses and need to support modern applications that benefit from IPv6 features. Google Cloud's IPv6 implementation is elegant and practical. You don't create IPv6 only subnets. Instead, you enable IPv6 on existing IPv4 subnets, making them dual stack. Resources get both IPv4 and IPv6 addresses. The critical decision is choosing between internal and external IPv6. This choice fundamentally affects how your IPv6-enabled resources can communicate with the Internet and with each other. Internal IPv6 uses unique local addresses, or ULAs, from the FD20:/48 range that Google assigns to your organization. These addresses are not routable on the public Internet. They're for private communication within your VPC and connected networks. External IPv6 uses globally unique, publicly routable addresses that Google assigns from their allocation. Resources with external IPv6 addresses can communicate directly with the public Internet over IPv6. This decision affects everything: firewall rules, routing, hybrid connectivity, and application design. You need to understand the implications before enabling IPv6 on production subnets. IPv6 internal versus external architecture. Let me explain the architectural differences between internal and external IPv6 because this decision affects your entire network design. With internal IPv6, Google assigns your organization a stable /48 ULA range. Each internal IPv6 subnet gets a /64 from this range. The key benefit is predictability. Your IPv6 addresses don't change and aren't dependent on Internet routing. Internal IPv6 is perfect for backend services, databases, and microservices that need to communicate with each other but don't need direct Internet access. Think of it as the IPv6 equivalent of RFC 1918 addresses. External IPv6 gives you globally unique addresses from Google's public IPv6 allocation. These addresses are routable on the public Internet, which means your services can be reached directly from anywhere in the world over IPv6. The architectural implication is significant. With external IPv6, You need to think carefully about firewall rules and security because your resources are directly internet reachable over IPv6. With internal IPv6, you get the benefits of IPv6 without the internet exposure. You can mix both types within the same VPC. Maybe your web tier uses external IPv6 for internet connectivity, while your database tier uses internal IPv6 for private communication. Implementing IPv6 in practice. Let's walk through the practical implementation of IPv6, because the commands and concepts are different from IPv4 in important ways. The key parameter is IPv6 access type. This determines whether you get internal ULA addresses or external publicly routable addresses. This decision cannot be changed after subnet creation, so plan carefully. For the virtual machine creation, notice the stack type parameter on the network interface set to IPv4_IPv6. This tells Google to assign both IPv4 and IPv6 addresses to the virtual machine. The virtual machine becomes dual stack. IPv6 firewall rules are separate from IPv4 rules. This is crucial for security. Enabling IPv6 on a subnet does not automatically apply your existing IPv4 firewall rules to IPv6 traffic. You must create new rules specifically for IPv6. The source range syntax is different. $0 means all IPv6 addresses, which is equivalent to quad 0/0 for IPv4. IPv6 addresses are much longer and use colons instead of dots. From a troubleshooting perspective, you'll need to use IPv6 aware tools. The IP command shows both INET, which is IPv4, and INET6, which is IPv6 addresses. Network monitoring and logging systems need to be configured to handle IPv6 addresses. Integration with existing systems is often the biggest challenge. Make sure your applications, monitoring tools, and security systems are IPv6 ready before enabling it in production. IPv6 best practices and integration. Let me conclude this section with IPv6 best practices that will help you avoid common pitfalls and integration challenges. First, always plan your IPv6 deployment as part of your overall network strategy. Don't just enable IPv6 because you can. Have a clear reason and plan for how it integrates with your existing infrastructure. For hybrid connectivity, remember that IPv6 ranges can be advertised over Cloud VPN and interconnect, just like IPv4. But your on-premises equipment must support IPv6 routing and have compatible IPv6 addressing schemes. Security is critical. IPv6 often bypasses traditional network security tools that were designed only for IPv4. Ensure your firewalls, intrusion detection systems, and monitoring tools are IPv6 capable. Application compatibility varies widely. Some applications work perfectly with IPv6, others need configuration changes, and some simply don't support it. Test thoroughly before production deployment. Monitoring and troubleshooting require IPv6 aware tools. Make sure your network monitoring, logging, and diagnostic tools can handle IPv6 addresses and traffic patterns. Start with internal IPv6 for your backend services. This gives you experience with IPv6 without the complexity of internet exposure. Once you are comfortable, you can move to external IPv6 for internet-facing services. The key is gradual, planned adoption, rather than trying to enable IPv6 everywhere at once. Alias IP ranges deep dive. Now we're getting into one of the most powerful and often misunderstood features of Google Cloud networking: alias IP ranges. This is where VPC native networking really shows its sophistication. The fundamental concept is that a single virtual machine instance can have multiple IP addresses from different subnet ranges. This isn't just about having multiple network interfaces. It's about having multiple IPs on the same interface, all coming from secondary ranges defined on your subnet. Think about why this is powerful. In traditional networking, If you wanted a virtual machine to serve multiple services with different IP addresses, you'd need multiple network interfaces or complex routing. With alias IPs, you can assign dozens of IP addresses to a single virtual machine, each serving a different purpose. For GKE, alias IPs are absolutely critical. Every pod gets an alias IP from the pod secondary range. But the applications go far beyond Kubernetes. You can use alias IPs for load balancer backends, for running multiple services on a single virtual machine, or for gradual IP migrations. The key insight is that these alias IPs are first-class citizens in your VPC. They can be reached directly from other virtual machines, from on-premises via VPN, and they show up in VPC flow logs. Multi-pod CIDR Advanced Strategy. Multi-pod CIDR is an advanced GKE feature that solves a very specific but critical problem: pod IP exhaustion in large clusters. Let me explain when and why you need this. In a standard GKE cluster, all pods across all node pools share the same secondary IP range for pods. This works fine for most clusters, but consider a scenario where you have thousands of nodes and tens of thousands of pods. The challenge becomes more complex when you have different types of workloads with different pod density requirements. Maybe your CPU-intensive node pool runs 10 pods per node, but your memory-optimized node pool runs 50 pods per node. Multi-pod CIDR lets you assign additional pod IP ranges to specific node pools. This means you can give your high-density node pools their own dedicated IP space, preventing one node pool from consuming all the pod IPs and starving other node pools. It also enables more sophisticated network policies and traffic engineering. You can route traffic differently based on which pod IP range it's coming from, or apply different security policies to different pod ranges. The implementation requires careful planning because once you enable multi-pod CIDR on a node pool, you can't easily change it. Network policies and micro-segmentation. Network policies are Kubernetes shared VPC integration patterns. Shared VPC is one of the most important organizational patterns for large enterprises using GKE, and understanding it is essential for the network professional exam. The fundamental problem shared VPC solves is IP address management and network connectivity across multiple projects. Without shared VPC, every project has its own VPC networks, leading to IP conflicts and complex peering arrangements. With shared VPC, you designate one project as the host project that owns the VPC networks, subnets, and IP ranges. Other projects become service projects that can use those shared subnets to deploy resources. For GKE specifically, this means you can have a centralized network team managing all the IP allocations, firewall rules, and hybrid connectivity in the host project, while application teams deploy GKE clusters in their service projects using the shared subnets. The network architecture becomes much cleaner. All your GKE clusters across different projects can communicate directly because they are in the same VPC. You have one set of firewall rules to manage, one hybrid connection to on-premises, and one IP address management system. The permission model is sophisticated. You can grant specific IAM permissions that allow service project admins to use specific subnets without giving them broader network admin rights. Load balancing and ingress strategy. Load balancing in GKE involves multiple layers and types, and understanding the differences is crucial for designing scalable, performant applications. At the highest level, you have external load balancers that provide public internet access to your services, and internal load balancers that provide private access within your VPC or connected networks. Google Cloud HTTP/HTTPS load balancers are global and anycast. Traffic is routed to the nearest healthy backend regardless of which region the user is in. This is powerful for global applications, but requires understanding how traffic flows and how to configure health checks properly. For GKE specifically, you have multiple ingress options. The Google Cloud Load Balancer Ingress Controller creates external load balancers outside your cluster. Nginx or other ingress controllers run inside your cluster and typically sit behind a load balancer. Internal load balancers are particularly important for microservices architectures where you want service-to-service communication to stay private but still be load balanced and highly available. The networking implications are significant. External load balancers can serve traffic from internet clients directly to your pods using VPC native networking. Security best practices. Security in GKE networking involves multiple layers, and getting this right is essential for production deployments. Let me walk through the key security principles. Defense in depth is critical. You need security at the VPC level, the cluster level, the pod level, and the application level. No single security control should be your only protection. Private clusters are the foundation of good security. By eliminating public IP addresses on your nodes and using private control plane endpoints, you dramatically reduce your attack surface. But private clusters require supporting infrastructure. Cloud NAT for internet access, private Google access for reaching Google APIs, and carefully designed access paths for administrators. Workload identity is crucial for securing how your pods access Google Cloud services. Instead of storing service account keys in your containers, Workload Identity maps Kubernetes service accounts to Google service accounts using IAM network policies provide microsegmentation at the pod level. Even if an attacker compromises one pod, network policies can prevent lateral movement to other parts of your application. The key is implementing multiple layers that complement each other rather than relying on any single security control. Monitoring and observability. Effective monitoring of GKE networking requires understanding the different layers and data sources available to you. This is where network engineering meets DevOps practices. VPC flow logs are your foundation for network visibility. They capture information about every network flow in your VPC, including pod-to-pod traffic within your GKE clusters. This gives you the ability to understand traffic patterns, detect anomalies, and troubleshoot connectivity issues. But flow logs generate enormous amounts of data, so you need to be strategic about sampling rates and filtering. For production clusters, you might sample 10% of flows but capture 100% of denied traffic for security analysis. Cloud monitoring provides metrics on network performance, but you need to understand which metrics are most important. Pod network utilization, service endpoint health, and load balancer backend health are typically your key indicators. Distributed tracing becomes critical in microservices architectures where a single user request might traverse dozens of pods. Tools like CloudTrace can show you exactly how network latency affects your application performance. Alerting should be based on SLIs that matter to your users, things like API response times, error rates, and availability. Troubleshooting network issues. Network troubleshooting in GKE requires a systematic approach because there are so many layers where problems can occur. Let me give you a framework for approaching these issues. Start with the symptoms and work backward. Is the problem with external connectivity, pod-to-pod communication, service discovery, or something else? The symptoms help you focus on the right layer. For connectivity issues, always check the basics first: DNS resolution, firewall rules, and routing. Use kubectl to verify that services are healthy and endpoints are populated correctly. VPC flow logs are incredibly powerful for diagnosing network issues. You can see exactly which traffic is being allowed or denied, track the path of specific flows, and identify bottlenecks or unusual patterns. For performance issues, look at both the network layer and the application layer. High network latency might be due to cross-region traffic, inefficient load balancer configuration, or application-level issues like database query performance. The kubectl command line is your primary tool for cluster-level diagnostics. Commands like kubectl get endpoints, kubectl describe service, and kubectl logs can reveal configuration problems or application errors. The key is having a systematic approach and understanding how the different layers interact with each other. Performance optimization. Network performance optimization in GKE is about understanding where bottlenecks occur and how to design your architecture to minimize them. This requires thinking about both the infrastructure and application layers. Proximity is fundamental. Keep related services close to each other. If your web tier needs to make dozens of calls to your API tier, make sure they're in the same zone or at least the same region. Cross-region network calls add significant latency. Node pools and placement policies can help with this. You can use node affinity and anti-affinity rules to ensure that related pods are scheduled on nearby nodes, or to ensure that critical pods are spread across zones for resilience. Load balancer configuration significantly affects performance. Global load balancers provide low latency by routing to the nearest healthy backend, but you need to configure health checks properly and understand how backend selection works. Connection pooling and keep alive are critical for microservices architectures where services make many calls to each other. Configure your applications and service meshes to reuse connections rather than establishing new ones for every request. Monitor your network utilization and identify hotspots. If certain nodes or pods are handling disproportionate traffic, you might need to adjust your scaling policies or traffic distribution. Exam preparation and key takeaways. Let me wrap up with the most important concepts for the GCP Professional Cloud Network Engineer exam, focusing on what you need to master for GKE networking. Understand the IP addressing fundamentals deeply. The three distinct ranges for nodes, pods, and services. How VPC native networking works with alias IPs. And how to plan IP allocations at enterprise scale. This is the foundation everything else builds on. Master the security models. Know when to use private versus public clusters. How to implement defense in depth. And how different security controls like workload identity, network policies, and VPC firewalls work together. Be able to design for different scenarios. Small development clusters, large production environments, multi-region deployments, hybrid connectivity with on-premises. Each scenario has different requirements and trade-offs. Understand the operational aspects, how to monitor network performance, troubleshoot connectivity issues, and optimize for different application patterns. The exam will test your ability to solve real-world problems. Know the integration patterns, shared VPC, load balancing options, ingress controllers, and how GKE fits into broader Google Cloud networking architecture. Practice with real scenarios. Set up clusters, break them, fix them. Implement network policies, configure load balancers, integrate with on-premises networks.